fourth video on a course on machine learning brought to you by my uh, YouTube channel AINEXUS. Please do subscribe to it. I am Dr. TV Geet. Now, in this particular video, we will be talking about probability, statistics, and information theory for machine learning. We will be giving the mathematical concepts and how it is connected to machine learning. In this video, we will also be talking about some exercises that we would like you to do. And these exercises are also provided in this video for the first video 3 on linear algebra and calculus. The exercise for that is provided in this video. Now, first, what are the learning objectives? We are going to explain the fundamental concepts of probability, information theory, and statistics that is used in machine learning. So, probability distribution, Bayes theorem, entropy, information gain, statistical measures, how to interpret uncertainty, and how to analyze machine learning with these concepts are all discussed here. So let's start with introduction to probability. So probability has to do with a random experiment. A random experiment is a process whose outcome cannot be predicted with certainty, even though all the possible outcomes are known. And tossing a coin, rolling a dice, and so on. Now, sample space is the set of all possible outcomes of a random experiment. Coin toss, you have only sample spaces H and T. Rolling a dice, the sample spaces 1, 2, 3, 4, 5, 6, and so on. Then comes events. An event is a subset of the sample space. So, for example, getting an even number when rolling a dice is 2, 4, 6. So, this E is a subset of S of the previous one. So type of events, there is simple event, compound event, mutually exclusive events, independent events. There are different types of events. Then the probability rule. The probability of event is the probability of E is the number of favorable outcomes divided by the number of total outcomes. So one is the probability of any event is between 0 and 1, and the probability of the sample space is 1, of null is 0, and complement rule is the P of E dash is 1 minus P of E. For example, if you take this events, even number rolling on a dice, P of E dash will be rolling the odd number. So you also have complement rule and addition rule. Addition rule is P A union B is P of A plus P of B minus P A intersection B. All these concepts you have studied in school. We are just reminding you. Then you have a very important concept as far as machine learning is concerned, and that is conditional probability. Conditional probability is the probability of an event occurring given another event has already occurred. And it is given by this equation. P of A given B is P intersection B by P of B. Please remember, this is very important for machine learning. So example would be, what is the probability of a king occurring given a face card? So the number of, so that is 4 by 12. Probability of A intersection B, that is 1 by 3. So now as far as machine learning is concerned, predicting uncertain outcomes like spam detection and so on. Sample space, all possible classes, event specific prediction. For example, customer buys a product. Decision making under uncertainties probability rule. Many of the important machine learning algorithms like Naïve Bayes classifier and all recommendation system are based on conditional probability. Then comes the probability distributions. So you have random variables again here. Random variable is a numerical value that is outcome of random experiment. You have discrete random variables and also continuous random variables. So discrete, the number of head in coin tosses, 5 coin tosses, height of a person is continuous. Discrete versus continuous describe a probability mass function of this sort. So P of x is equal to x for all possible x's. What is that? Described by a probability density function. F of x is greater than or equal to 0, minus infinity to plus infinity, f of x dx is equal to 1, given like this. These are two important distributions. Now let's look at important probability distribution. The first is Bernoulli distribution. It models a single trial with two outcomes. You know what that is. Like for example, a toss of a coin. So 0 is 1 minus p and 1 is p. This is the simplest distribution. Then is the binomial distribution. Models the number of successes in n independent Bernoulli trials with success probability p. So, for example, it is given in this way. So, example, number of heads in n coin tosses. That's the simplest way of explaining this, and this is the formula for that. I'm not going into the formulas in detail because all this you have studied already either in school or in your college maths, but just to bring it up, and when you have any doubts, you can look at these videos again. The most important distribution as far as machine learning is concerned, which I am bothered about, is the Gaussian normal distribution. The most important continuous distribution. It is symmetric and bell shaped, and the mean is mu and the variance is given here. So height of people measured, noise, errors, and so on. So here is the comparison of the three distributions. So basically the use case is single success failure for Bernoulli, count of successes in n trials is binomial, and natural phenomena is Gaussian. It's also called normal distribution. These distribution is a foundation of many machine learning algorithms. Then comes the famous Bayes theorem. As I tell my students, Bayes theorem you have to, eat, sleep, dream Bayes theorem, because Bayes theorem is very important in machine learning. It's used in many applications. So Bayes theorem is given as the conditional probability. The probability of A given B is the probability of B given A into the probability of A by the probability of B. Now each of these terms here have specific meanings. So A is the hypothesis, E is the evidence, B is the evidence, B is given. P of A is prior probability. What is the probability that A will occur generally? And P of B comma A, that is probability of B given A, is called the likelihood. And probability of A given B, what we want to find out, is called the posterior probability. This is the simple Bayes theorem. The probability P of A is the probability of the hypothesis before seeing any evidence. What is the probability of something occurring? Okay. Before analyzing an email, the prior probability that it is spam might be 20%. Posterior probability is the probability of the hypothesis after observing the evidence, in this case B. Example, after seeing the email contains the word free, the probability of the spam increases, that it being spam increases to 67% or 0.67. This is likelihood. The likelihood is the probability of observing the evidence given the hypothesis, given a particular hypothesis, where all evidence will be there. Example, if a spam email is spam, the probability of it containing the word free. Please understand the difference between likelihood and posterior. Bayesian inference uses this Bayes theorem to update the probability of a hypothesis as new evidence becomes available. So it allows models to learn from data iteratively and have better performance, which is one of the definitions of machine learning. So there is an example of spam filtering here. It is given that P of spam. What is P of spam? Probability that it is spam. Prior probability is 0.2. The probability of free given spam, which is the likelihood, is 0.2. And the probability of free not spam is 0.1. So this is how it is found using the probability rules. Similarly, you can do for medical diagnosis. Then comes expected value and variance. So expected value or expectation is the average or long-term expected value of a random variable over many repeated experiments. So E of x is equal to summation of xi pi, and if it is continuous, it will be given in this way. And you can find that for a fair dice, this will be the value. I'm not showing you how to calculate the value. Actually, over many rolls, it is 3.5, but a single roll will never give you 3.5. That's a different question. Then next comes variance. Variance measures how much the value spreads around an expected value. So variance is E x minus mu squared, or it is given in this way where mu is equal to E of x. Then, so interpretation is, if it is low variance, values are close to the mean. If it is high variance, values are widely spread. A student scores 70, 80, 80, 82, then it is low variance. If student B scores 50, 80, 110, then it is high variance. So next comes uncertainty. Uncertainty represents the lack of confidence about an outcome. Low uncertainty means the model predictions are consistent. High means obviously predictions will vary significantly. So low uncertainty, 90% chance of rain. High uncertainty, 50% chance of rain. You are actually not predicting anything. Higher uncertainty means you are less confident about the result. Then comes risk. Risk combines the likelihood of an event with its potential impact. So loan approval, risk of borrower defaulting, fraud detection, risk of fraudulent transaction, and so on. So higher variance often indicates, we have seen variance, higher variance often indicates higher risk, because variance means its values are widely spread, so the risk is more. Prediction confidence, which is very important in machine learning, indicates how certain a machine learning model is about its prediction. Image classified as called 99% confidence means it's good, like that. And generally indicates a more reliable prediction. So basically, expected value is used for the expected reward in reinforcement learning. Variance measures model stability. Uncertainty quantifies confidence in prediction. Risk is based on the confidence variance, and prediction confidence gives you the confidence of how good your prediction is. So this is the importance of this. Then comes applications. I'm not going into detail, just to give you a feel. Naïve Bayes can help you to do spam filtering. Hidden Markov models. I'm not going to the example, but we have many probabilities here. And it's a probabilistic model for sequential data where the system beginning model is assumed to be a Markov process with hidden states. So I will not go into detail. This is basically used in speech recognition. All this uses probability. Bayesian network is a probabilistic graphical model representing a set of variables, and this can be used for diagnosis prediction. Anomaly detection uses probability to identify data points that are unlikely under the normal behavior of the system. So that is an example. Probabilistic classifiers. These models output the probability of each class and makes prediction based on the highest probability. So these are examples where probability is used. Naïve Bayes is the simplest one, where the prior probability is calculated. Next comes descriptive statistics. Here we have these terms. All this you know, so I'm not going to go in detail. Mean, median, mode, variance, and standard deviations. All these are very important for a lot of data pre-processing applications also. Skewness measures asymmetry of the data distribution. So skewness equal to 0 means symmetric. It is equal to greater than 0 means right skewed. Lesser than 0 means left skewed. And the skewness is calculated like this based on mu and variance. Then comes feature scaling or normalization. So you have min-max scaling, which we will go into detail when we're doing data processing. So scales into a fixed range, and standard scaling is also there. Transform data to have a mean of 0 and standard deviation of 1. So central tendency is given by mean, median, mode, dispersion, variance, and standard deviation. Shape, skewness, and scaling is the feature scale. Then we have correlation, sampling, and statistical inference. Correlation measures the strength and direction of the relation between two variables. Here we are talking about two variables, x and y. So positive correlation means both variables increase together. Negative correlation, I'm not going into the equations in detail here, because that you can look at. You may have studied in both school and college also. Negative is one variable increases while the other variable decreases, and zero correlation means there is no linear relationship. So this is an example. Covariance indicates whether two variables change together. Positive covariance means variables move in the same direction. Negative covariance, they move in opposite directions. Zero means little or no relationship. So machine learning uses this for feature analysis and principal component analysis. Then comes sampling. Sampling is the process of selecting a subset of data from a larger population for analysis. There is random sampling, stratified sampling, and systematic sampling. So surveying 1,000 customers from a population of 1 lakh to estimate the customer satisfaction. That to get that you do sampling. It saves time and cost and enables learning from large data sets. Next is confidence intervals. A confidence interval provides a range within which the true population parameter is likely to lie. That is, if you have the range within which it will lie. So we are 95% confident that the true average age lies between 33 and 37. So that is the confidence interval. Then comes hypothesis testing. Hypothesis testing determines whether the observed results are statistically significant. Null hypothesis means no significant difference. H1 is an alternative hypothesis, significant difference results. So when a new algorithm comes, you have an existing model and a new model. Okay, so you want to know whether the new model is better. So that's how you do. Then you have p-value, which measures the probability of obtaining the observed result if the null hypothesis is true. So you have a decision rule. If it's less than 0.05, reject the hypothesis. If it's greater, fail to reject H0. It's not statistically significant. So applications, correlation is used for feature selection and identifying relationship, covariance for dimensionality reduction, sampling during training, validation and all that. Confidence intervals, estimated model accuracy, hypothesis testing, comparing the machine learning algorithms and so on. Then we go to applications. So you use it for data pre-processing as we already told. Then we use it for feature selection. We use it for model evaluation. We use it for cross-validation. We use it for performance metrics and we use it for uncertainty estimation also. The details are given here. Then we come to the final one in this particular topic here is entropy and information gain. This comes from information theory. So entropy is a measure of impurity. Entropy measures the randomness or impurity in a data set and is given like this. H of S is equal to I is equal to 1 to C minus PI log to PI, where S is the data set and PI is a proportion of class I in S. So entropy value 0 means all belong to the same class. Higher value means it is more impure, maximum for balanced classes. So if a data set contains 10 samples, 6 are positive, 4 are negative. P of positive is 0.6 and P of negative is 0.4. So the entropy is given like this. Next you have information gain. Information gain measures the reduction in entropy after splitting the data set on an attribute. Okay, it is given by this formula. Here A is the attribute. S of V is a subset of S for value V of A. SV is the number of samples and S is the total number of samples. So that's how you calculate this. Higher IG, information gain, means it's a better split. Ig equal to 0 means there is no improvement with the split. If you choose attribute with the, you should choose the attribute with the highest Ig. So you can calculate the information gain in this way. So split, we'll be doing this in detail when we are talking about decision tree basically. So data set contains 10 samples and HFS is given. Split on attribute A, yes. These are the samples and you can calculate the information gain as given equal to 0.257. And how it works in a decision tree is given here. Compute IG for all attributes, split on best attribute, subset become more pure. Repeat until nodes are pure. So this is basically why we spoke about this information theory, mainly for understanding decision tree, which we will do later. Now let's look at some references. First, I'll give you references and exercises in linear algebra and calculus. These are the references. I've given both references, books as well as online resources. Some short questions and descriptive questions for you to understand what we have done, summary, and some problems also I've given. Okay. Then I have given some mini projects, including, you know where to get the data set. We have seen before in a video. So I've given house price prediction, and you're using Python for it. Student marks prediction, principal component, and for dimensionality reduction and image compression. And another movie recommendation and linear regression. Similarly, I've given you for probability statistics and information theory, references, online resources, and some exercises, short and long questions, problems, and then mini projects also, medical disease and predicting analysis of student performance and predicting customer behavior and stock market. I strongly advise you to please do the mini projects also and the problems also. And in the next video, we'll be talking. Maths is over. So we finished 3 and 4. We spoke about maths. Here we're going to talk about data pre-processing, missing values, encoding, scaling, and feature engineering. So please do subscribe to my YouTube channel, PVG Nexus, in which there is a separate playlist on course on ML. So please do go there and check out all the videos. Subscribe to the channel.